Hello and welcome to my tutorial on the reactions of halogenoalkanes. So the halogenoalkanes are any alkane with a halogen, any of the group 7 elements, except for astatine because it's radioactive, and also because it's in such low abundances we cannot analyse the chemistry of it yet unless we find a massive deposit of it. Anyway, so they react like this by using the nucleophilic substitution reaction mechanism, in which a group of atoms or unatom by itself is replaced by a nucleophile, which is an electron pair donor. So the hydroxide ion, an OH minus, has a lone pair. So if we just draw that, so it's a lone pair like that. And they're attracted and donated to the electron deficient carbon atom in the halogenoalkane, which is here. And it's also known as nucleophilic attack, because the lone pair is attacking the the electron deficient carbon atom, and the donation of the electron pair leads to the formation of a covalent bond between the oxygen atom of the hydroxide ion and the carbon atom. So it will form a new alcohol, and the carbon halogen bond breaks by heterolytic fission. The electrons from the bond move to the halogen, making the iodine an I- ion. Because the carbon iodine bond breaks as the two electrons in the covalent bond move to the iodine, forming the ion. So electron pair, these arrows are representing the electron pair movement. So two electrons from the oxygen are moving to the carbon, and by that happening, so this is like step 1, and step 2 here is the bonding pair of electrons moving to the iodine atom, as it has room in its outer shell for one more electron. So this cross is representing the bonding electron that came from the carbon, but now it's turned iodine into a minus ion. And the conclusion to the reaction is as follows on the right. So really, a nucleophilic substitution is a type of substitution reaction in which a nucleophile is attracted to an electron deficient carbon atom, where it donates a pair of electrons to form a new covalent bond. So we're now going to talk about the rate of hydrolysis for primary halogenoalkanes. And when you heat a halogenoalkane with silver nitrate with ethanol, the ethanol will act as a solvent, and it makes sure the halogenoalkane and the silver nitrate mix together and react. This ionic equation represents the overall reaction that happens when you add silver ions and chloride ions to form a white precipitate silver chloride. But this is the overall reaction, where the H plus ions and the Cl minus ions are formed when you have this halogenoalkane plus H2O. I'll put ethanol as a reaction conditions because both of the reactants are in ethanol. So this alcohol will form. So 1, 2, 3, 4. That'll be butanol. And H plus ions and Cl minus is form, and this is the main precipitate that will form if you have a closer look at the reaction vessel. So this is hydrolysis, and the rate of reaction increases as the carbon to halogen bond weakens. So as you go down group 7, the polarity of each halogen to a carbon atom weakens. So as I get to iodine, the bond is so weak it requires little energy to break the bond. So if it requires a minimal amount of energy, then the rate of reaction will increase as less energy is required to be put into the system. So if we look at these precipitation reactions and the polarity versus the bond energy, but not all at once, the halogenoalkanes form different precipitates. So using the same sort of reaction mechanism as I showed you in the previous slide, chloroalkanes will form AgCl, white precipitates, as in the example. Bromoalkanes form silver bromide, and they form a cream precipitate. And iodoalkanes form silver iodide with a yellow precipitate. And bond enthalpies, the strength of the carbon-halogen bond decreases down group 7, as I explained earlier. Iodine will require the least amount of energy to break the bond, so the rate of reaction is the fastest. So the actual energy stored in the chemical bond between the carbon and the iodine atom is for a very low amount. So in terms of electronegativity, the carbon atom would have the bonding electrons more than the iodine, as the iodine isn't really putting up much of a fight in terms of electronegativity. And we also look at this graph. We can see in reverse order that the carbon to fluorine bond is the strongest and it has the most amount of enthalpy. So I'll say that's about 500, and in comparison to a carbon to hydrogen bond, it's slightly more than a normal carbon to hydrogen bond. So carbon to fluorine will require more energy, as fluorine is the most electronegative atom on the periodic table. So definitions: polarity affects the rate of hydrolysis, so the carbon delta positive attracts the nucleophile more readily and gives the fastest reaction. So this is the key word. The nucleophile is attracted more readily and it gives the fastest reaction if less energy is required to break those bonds in the first place. So bond enthalpy, the carbon iodine bond is the weakest, so the bond requires less energy to break. Less energy input means a faster reaction. So that's it for this tutorial. It's not really asked in exam questions, but what you do have to appreciate is that this is your F321 knowledge applied to organic chemistry. So if you want more information on the halogens, you need to go back in time to F321. So if you head to my channel playlist for OCR Chemistry Unit 1, then my tutorials should remind you if you have forgotten all about the halogens and their different properties. But the main properties in terms of organic chemistry are the rates of hydrolysis, their polarity, and their bond enthalpy. Bond energy and bond enthalpy are exactly the same thing, so it's best just to remember it as enthalpy, so as not to confuse anyone. Bond energy and bond enthalpy are exactly the same thing. It's just they're very interchangeable. Your chemistry teacher will probably interchange their words quite a lot when they are talking about it, but they will say enthalpy, hopefully more than energy. So thanks for watching and goodbye.